Hello friends, welcome to the course Exploratory Data Analysis for Data Science with R Software. You can recall that in the last lecture we initiated a discussion on finding out a mathematical relationship using statistical tool when the variables have got some association. And we had understood the principle of least square, and we have seen that how we can obtain the values of the parameters of a linear model using only the data set on input and output variable. And we had done all the calculations manually to understand the process. Now, in this lecture, we will continue on the same topic, and I would like to first show you that how the same calculation which you did manually in the earlier lecture can be done using the R command. And the more important part is how to interpret it, how to understand the outcome of the R software. Second thing will be, I had tried my best to give you the basic idea behind the statistical modeling by considering only one input variable. But usually in practice, in real data, there are more than one input variables which are say impacting the values of y. So here I would try to show you a very brief introduction that if you have more than one independent variable, how are you going to handle them? And how are you going to take the outcome in the R software? Definitely this whole area comes under the say statistical modeling of through linear regression model, and but here my objective is very simple. I am not going into that much detail, but I want to show you that that how the EDA tools or how the tools which you have learned in the exploratory data analysis can be extended to different statistical modeling, right? And before that, can you recall one thing? You had found the relationship between x and y in the earlier lecture, and you had in the examples you have considered only the continuous variable. So if you want to see, you are essentially using the aspect of correlation coefficient to determine the level of association or the degree of association between the two variables linearly, and then you also learned that how to express them in a mathematical way. The same thing you have to keep in mind when you are trying to do when you are trying to extend it for the case when the outcome variable is being affected by more than one input variables. So let's begin this lecture and try to understand this concept in more detail. So you can recall that in the last lecture we initiated a discussion on the concept of linear models, and we had considered a linear model in the framework of y equal to alpha plus beta x, which was very much similar to the equation of a line y equal to mx plus c. And we had learned that how we can estimate the values of alpha and beta on the basis of given set of data, and then we had obtained a weighted model. Weighted model means the model in which we have obtained the unknown values of alpha and beta on the basis of given set of data. And for that you had used the principle of least square. After that we had made all the calculations manually. So now in this lecture I would like to show you that what are the R commands for finding out the same model which you obtain manually. So in R software there is a command here LM. LM means linear models. So linear model is the command to fit the linear models and to obtain the models in a mathematical way or a statistical way. So it has different options. For example, you have to write LM, then you have to write the formula. Formula means you have to express the independent and dependent variables in a particular way. I will try to show you. And then you have to give the data, you have to subset, weights, NA dot action. There are many options, right? But I would request you to go to the help menu and try to understand these options depending on the requirement. In this lecture we will formula, actually you try to use this formula which is a sort of symbolic description of the model to be fitted, and you try to give the independent and dependent values in a way so which R can understand and can give you the fitted model. Then you have the option of here data. This is an optional data frame or list environment, or which contains the observations on the variables in the model. Then you have here subset. It is an optional vector specifying a subset of observation to be used in the fitting process. That means you do not want to use all the data, but you want to use only a subset of the data, and so on. There are many other, but now let us come to our job. And you can recall that in the last lecture I had considered this example where we have collected the data of 20 students on the obtained marks out of 500 in an exam, and the data on how much they have studied in a week. So, and we know from our experience that when students are studying more, then they get more marks. So, so there has to be an increasing trend that as the number of hours of studies are increasing, the marks should also increase up to a certain extent. Yeah. So, the data is like this. For the student number 1, if the student is studying 23 hours, the student is getting 337 marks out of 500. The second student is studying 25 hours and getting 316 marks out of 500, and so on. Right. And in the last lecture, you had computed these values x bar, y bar, beta hat, alpha hat, and you had obtained the model, say marks is equal to 168.65 plus 6.3 hours. So, I am not going to repeat it, but just want to recall you and want to show you that the same values you will get through the software also. So, now we store this data on marks and hours in two data vectors, and what is their interpretation, that is we already have discussed in the earlier lecture. Now, I use here the command, but the more important part is you have to see how I am using this command. So, I am using here the command lm, and then if you try to see, I am writing here marks and this symbol tilde. The quicker symbol is available on your keyboard. So, I will write down here lm, the dependent variable or say output variable y, and then here tilde sign, and then here this x independent variable. And so, I write down here say this, and then I get here this outcome. It will be like here lm formula is equal to marks tilde hours. So, this is how you have to interpret that this is your here output variable and hours is your here input variable. Now, you are getting here the coefficients. So, first coefficient here is intercept and second is about hours. So, interceptum, if you try to recall, this was your alpha hat. So, this is the value of here alpha hat 168.647, and this was like y bar minus beta hat x bar, and this beta hat is obtained here. This is beta hat summation xi minus x bar yi minus y bar upon summation xi minus x bar whole square. I goes from 1 to n. Right. And you can see here that in your earlier case also, your this alpha was 168.65 and beta hat was 6.3. Right. So, now based on that, you can write down here your model like as y is equal to say here alpha, which is here 168.647 plus 6.304 into x, or I can say here mark is equal to 168.647 plus 6.304 into hours. So, this is the same model that you had obtained earlier, you can see here. Now, this model can be used for different purposes, different jobs, and then you can infer different types of interpretation. For example, this hours is going to give you the value of rate of change in the average value of y when the value of x changes by 1 unit. So, this means in case if a student increases the number of hours of study by 1 hour, then the marks are going to be increased by say approximately 6.3. And similarly, when you are trying to look at the value of here intercept term, this is actually the average value of y when all x's are equal to 0. So that means in case if you say that the student has not studied at all, but still the student will get on an average 168 marks. Yeah, that is possible because the student might have studied from other resources or attended the classes or say possibly already knew that topic quite well, or say reasonably well. So these are different ways of interpretation of the data that you have to understand. And this is the screenshot here. So first let me try to show you these things on the R console so that you get here a confident. So I'm just trying to copy this data over here. So you can this is the data here, and after that I try to use here the command here lm marks tilde this hours, and you can see here this is the same outcome which I have shown you, right? Okay, so now let me try to come to one more aspect of this thing. You see, in this case I have considered the situation where only one independent variable is affecting the outcome y. But in practice, in real life, there can be more than one input variable which are affecting the outcome, right? For example, I had given you an example, say for example the crop. So yield of a crop will depend not only on quantity of fertilizer, but on say rainfall, temperature, irrigation and so on. Similarly, the marks of the student, they not only depend upon the number of hours of study, but they also depend on number of submitted assignment, number of hours spent in sports activities, etc. Right. So now I would like to extend the concept which I have explained you in the case of one variable to the case when there are more than one independent variables. Well, I will not be going into that much detail, but I want to show you how can you at least do the analysis using the R software, and how are you going to use the graphical tools and this analytical tools together, and what type of complications you can see when you are trying to analyze such a data, right? So now you can recall that we have considered earlier a model here y equal to alpha plus beta x plus e. So there was one input and one output, one input variable x and one output variable. Now I try to extend it. So I am just extending it the same model as suppose there are say p input variable, say x1, x2, xp. So I just extend it to y equal to alpha plus, now beta x is for one variable, so I just extend it to beta 1 x1 plus beta 2 x2 plus up to beta p xp and some random error. The e is your here random error. Now one basic fundamental assumption, you assume earlier that the y and x, they are linearly related. Now I am extending this assumption to more than p independent variable or more than one input variable x1, x2, xp. I assume that the relationship between y and x1, x2, xp, which is a group of variable, is linear. So that means the relationship between y and x1, x2, xp is a joint relationship, and we are assuming that x1, x2, xp, they affect the y jointly in a linear way, right? So now the first question whenever you are trying to handle such an issue comes, that how can you judge that whether there exists a linear relationship or something else, because when you are trying to increase the number of input variable, the complications increase. So in such cases different types of plots which we have discussed, they can be helpful. Now, what are those plots, how they can be used? This depends on your capability, your thought process and your experience, how you want to use them and take the correct outcome. Right. So, for example, we have considered earlier the matrix plot. They are also useful in verifying the linearity graphically. So, now what we try to do, we conduct an experiment and obtain n tuples of observation on the dependent or say output variable y and the independent or say input variables x1, x2, xp. The same way as we did in the case of say this simple linear model, y equal to alpha plus beta x plus e. And now I will say that, okay, now suppose you have here situation like the same example, I will say yield of a crop, and you try to say here quantity of fertilizer, irrigation, and here say temperature. Suppose I take a 3 variable. So, y here is yield of crop, quantity of fertilizer see here x1, irrigation x2 and temperature here x3, and now I conduct the experiment. I take some quantity of say x1 1 kilo of fertilizer. There is suppose x12 say centimeter of irrigation and the temperature was suppose x13 degrees, and based on that I get here a value y1. So, this experiment is repeated. Once again I take here one more set of say x21 kilo of fertilizer, x22 centimeters of irrigation and suppose x23 degrees of centigrade, and based on that I get a value here y2. So, I assume that all these values are going to satisfy the model, say something like alpha plus beta x1 plus beta 2 x2 plus beta 3 x3 plus e. Right. So, similarly now we are considering here x1, x2, xp. So, for each of the variable x1, x2, xp we have a set of observation, and we believe that each set of observation is going to satisfy the relationship. So, for the first set of observation I can write the model as y1 is equal to alpha plus beta 1 x11 plus beta 2 x12 up to beta p x1p plus e1. And similarly for the second set of observation I can write down here y2 is equal to alpha plus beta 1 x21 plus beta 2 x22 plus up to beta p x2p plus say epsilon 2. And similarly for the nth observation I can write down here yn is equal to alpha plus beta 1 xn1 plus beta 2 xn2 up to beta p xnp plus en. Now, do you remember that if I have here say equation like y1 is equal to 2x1 plus 3x2 and say here y2 is equal to 4x1 plus 5x2, then I can write down it in terms of here matrix and vector. So, I can write down here something like this way, the vector y1 y2 and then the matrix 2 3 4 5 like this one, and then the vector here x, right. So, the same thing I try to do with here all these equations, and I try to write them in the form of a vectors and matrices. So, all these values of y, y1, y2, yn, they are now in a n cross 1 vector, which is indicated here as a y. Then all the values of here these coefficients, they are here say here alpha, beta 1, beta 2, beta p and so on. So, this is a vector of order p plus 1 cross 1, and this is indicated by here beta. Now, all the values in this observation, the first column become here say 1, the second column become here x11, x21, xn1, and so called the pth column becomes here x1p, x2p, xnp. So, all these values they are written as say here x. So, x which is here a n cross p matrix, say here like this. So, x is a n cross p matrix of observation on p independent variable. So, there are altogether n observation on each of the x1, x2, xp. So, all these observations are combined in the matrix here x, which is of order n cross p. So, now this is my here model y equal to x beta plus epsilon, and you can recall that earlier we had written here s and then we had minimized summation ei square, I goes from 1 to n. So, if I try to write down here, then you can notice here that whatever I have written here as the n cross 1 vector of here as e1, e2, en, which I am indicating here as a e, So now this summation ei square can be written here as a E transpose E, right. So I try to write down here y minus x beta transpose y minus x beta, but you have to be careful now. Y is a vector, x is a matrix, and beta is a vector. And then I try to differentiate it with respect to beta, put it equal to 0. Then I get here beta equal to beta hat as x transpose x whole inverse x transpose y, right. And after that you can verify the second order partial derivative of s with respect to beta, beta is 0. So that means beta equal to beta hat is minimizing the sum of squares due to errors. So now you can see here that the value of beta hat what you have obtained, this is a sort of multivariate version of beta hat which you had obtained in the case of y equal to alpha plus beta x. This is called here as say the least squares estimator of beta. And you can see here it depends only on two types of variables. One is here the matrix x and the vector here y. So the observation on y vector y1, y2, yn they are available. The observations on x1, x2, xp, so this x is also known to us. So given this data we can compute the value of beta hat. And beta hat will be actually like here a vector quantity. If I try to write down here, this will be alpha hat, beta 1 hat, beta 2 hat up to here beta p hat, right. So now I will not go into the details of this algebra and further application, but I would like to show you that on the basis of given set of data, if you want to find out these values of beta hat, how can you do it, right. So suppose we consider here an example where we have two variables. So this data is obtained on the delivery time taken in delivering different parcels and the corresponding distance travelled by the courier person. So you know if a courier person has to deliver more parcel, it will take more time. If the places are far away, then where the parcels have to be delivered, then also it will take more time. Right. So this distance of locations and the number of parcels both are related to the time of delivery of the parcel. So this delivery time is recorded in minutes and number of parcels are in numbers, and then distance is measured in say meters. Yeah, that's a hypothetical data just to explain you, right. So the observation number 1 tells that the delivery person has delivered 7 parcels and had to travel 560 meters, and the delivery time was 16.68 minutes. Similarly, the second observation is the delivery person had to deliver 3 parcels and travel 220 meters, and the delivery time was 11.5 minutes. Similarly, in the case of third observation, there were 3 parcels to be delivered and the travel quick distance was 340 meters and it took 12.03 minutes, and such type of data is given over here. So now we will just store all this data into 3 data vectors, and for that the model will become like yi is equal to alpha plus beta 1 x1 I plus beta 2 x2 I plus ei, I goes from 1 to 25. So yi will become your here delivery time, which I am storing in a data vector here, say del time. Then x1 is your number of parcels which are delivered. So I store it as parcelno, that means parcel number of parcel, and the second input variable here is distance. So I am just trying to store all these data in 3 such different data vectors in the same order in which they have been given. For example, the first value 16.687 and 560 is indicating that the delivery person delivered 7 parcels, traveled 560 meters and took 16.68 minutes of time, and so on, right. So now if you have here three things, then you would like to find out here a model like del time is equal to alpha plus beta 1 into parcel NO plus beta 2 into distance. Right. So now how to do it? But before that you have to first verify if there is a linear relationship between y and x1, x2. So x1, x2 on one side and y on one side. So for that we have one option that we can create here a matrix scatter plot. So I can use here the command here PAIRS, pairs, and then after that you have to use the formula data subset. So X is the data set in the form of say columns of matrix or the data frame, whatever you want. Formula is something like formula the way we write say tilde x plus y plus z, where there are three this variable for which we try to create this matrix scatter plot, and then we have here the data and so on. So now let me try to show you this thing. So this, and then after that subset data or data frame, there are many options, but I would like to request you to please have a look in the help menu. Right. Now let me try to show you here, and our objective is that we are having only a sample of data, and based on that we are trying to take a conclusion about the entire population, and I have considered here only two variables which are affecting the outcome, but in real data set there can be more than two variables which are going to affect the outcome. So if you try to see, I write here the formula as say the command here is pairs, PAIRS, and then tilde del time plus parcel number, parcel NO plus distance, and then mean is given to give the title matrix plot or delivery time data, and I get here this type of graphic. So you can see here now we have understood that how are we going to read such graphic. So on the x-axis this is the data of say del time, then parcel number and distance, and on the y-axis this is again the same order del time, parcel number, and say here distance. So you can see here you want to see what is the relationship of say y, which is del time, with respect to parcel number, number of parcel, and distance. So if you try to see here the relationship between delivery time and distance is given here, and the same thing is here also, because you know this is a symmetric plot. So if you try to see here, there is it appears that there is a linear relationship between distance and delivery time. Similarly, if you try to look, your next objective is you want to see the relationship between delivery time and the number of parcels. So if you try to see here, this is the graphic here which is giving you the relationship between this parcel number and here delivery time. So this and this, they are the same, but if you try to see, there is here a sort of linear trend. So now you can see here that both the variables say parcel number and distance, they are showing that there is a linear trend in the values with respect to the time of delivery. So we can safely consider that okay, when they are working jointly, they are also expected to have linear trend, right? But if you want to be on the safe side, it is better option to take the help of some more graphics, whatever you know, right? So you can recall that we had considered the scatter plot 3D. So let us try to create the scatter plot 3D using the command scatter plot 3D del time, parcel number, and distance. So you can see here, this is coming out to be here like this. This is the data which is scattered here like this. And if you try to rotate its angle, right, so its angle, if I try to rotate by 120 degree, so this looks like this if data is coming over here. Yeah, but now I am getting some idea, but now I am not 100% fully confident how it is looking into the 3 dimension. So I try to use my here some more options over here, and I try to create here the scatter plot 3D, where I try to give here the colors to the point as blue and the size to be 10, and the type here is height. Say this so that I can see that how they look like in a horizontal plane. So I try to create the lines like that here in this one, so that I can get a better picture. And so there is a title plot of delivery time versus number of parcel versus distance x, y z axis I can have the title number of parcel, distance and delivery time to make it better and more informative. So, now you can see here it will look like this scatter plot 3D. So, now you can see here by looking at this point I am getting here a fair idea, and even on the plane you can see here that they are more or less here linear. So, I now become more confident that okay, I can use here the multiple linear regression model. That means I have two independent variables which are affecting y, but still I would like to be more confident. So, I can use here one more graphic which we have learnt, GG pairs. So, I try to create here this 3-dimensional this matrix scatter plot. So, now I try to gain more confidence. So, you can recall that we have done the one more type of matrix scatter plot using the command GG pairs, right. So, you can recall that in this case you had the 3 variables parcel number, distance and delivery time, and parcel number, distance and delivery time. So, if you try to see the relationship between delivery time and number of parcel, so you can see over here, it shows here a linear trend, and the corresponding correlation is also here 0.965, right. And similarly, if you try to look into the graphic of say delivery time and the distance, so you can see here this is here the like this one, and this correlation here is 0.875. So, this is here like this. So, I can see here there is a strong correlation between y and x1 and y and x2. So, I can believe I have more confidence that the joint relationship of x1 and x2 with respect to y will hopefully be linear. And this graphic has been created by this command that first I try to create a data frame using the command data.frame for parcel number, distance and del time, and I store it into data LM, and then I use here the library ggalley and GG pairs on this data LM. So, I get this one. So, you can see here by using different types of graphic I am getting more confident the model which I am going to fit will give me a good outcome. So, now I want to fit here a model yi is equal to alpha plus beta 1 x1 I plus beta 2 x2 I plus ei, I goes from 1 to 25. Now, I use here the command here lm. So, earlier if you try to recall you had written y tilde x. So, now what I have to do, I have to write here my y which is here del time and then tilde sign, and then I will say indicate all my independent variable here with the plus sign. So, I have here 2 independent variable, 2 input variable, number of parcel which is parcel NO and the distance which is here by distance. So, I write parcel NO plus distance, and if you have more than 2 variables then you can just use here plus sign and can give here all the variables. Now, you get here a outcome. So, this is the formula which has been actually used. Formula is equal to del time, tilde means something like here equal to parcel number plus distance and so on, right. So, what is the interpretation? So, you see here the first value here is intercept. So, this is here the value of here alpha hat. So, you can recall here that here beta hat will be something like alpha hat, beta 1 hat and say here beta 2 hat. So, these values are given here. So, alpha hat is equal to 2.19579. Similarly, if you try to see second value here parcel NO, this is the value of here beta 1 hat, and the third value here is distance. So, the distance here is the value of here beta 2 hat which is 0.01311. So, what are these values trying to indicate? The values are indicating, for example, let me start from beta 2 hat. Beta 2 hat is 0.01. So, here if you notice the sign is here actually plus in all these coefficients, right. I can tell you that if the sign is negative, that means the relationship is decreasing. So, this means beta 2 hat is 0.01311. So, that means when there is a unit change in the distance, then the delivery time increases by 0.01311 minute, and it is increasing. If this sign would have been negative, then I would say that the delivery time decreases. Similarly, if you try to look into this parcel NO, this value is 1.67803. So, I can interpret it, if there is one unit change in the number of parcel, that means if one parcel increases, then the time of delivery will increase by 1.67803 minutes. And similarly, in case if you try to see here at intercept term, which is plus 2.19, so I can say that if the value of parcel NO is 0, if the value of distance is 0, then even that the delivery time will be 2.19579. So, in this case, the model or the fitted model will become like del time is equal to 2.196 plus 1.68 into parcel NO plus 0.013 into distance. Right. So, by this you can actually compute that if the distance increases or decreases by this value, parcel number increases or decreases by this value, then what will be the delivery time and so on. So, this is your here fitted model, and this is here the screenshot of this same operation. So, let me try to show you these things on the R console actually, so that you get here more confidence, right. So, let me try to first copy all this data over here. So, this is my here the data, and now if you want to plot here these type of plots, you can see here this is my here matrix scatter plot, right, the same one which you have seen, but my objective was to show you that how you can combine the information on graphic and numerical values together to obtain such values. In order to create this 3-dimensional plot, I have to load my this library scatter plot 3D, and now I have to use here this command to create the scatter plot. You can see here it is here like this, and if you want to change its angle, then you have to add here angle is equal to 120. So, you can see here you get here this thing, and now if you want to create here more informative plot, then you can see here like this. I will give the same command, and you can see here this graphic is looking like this. So, by looking at the flat surface and the heights of these points, you can guess some more values, and that is what I always told you, that you have to practice so that you get better outcome. Now, if I want to create this diagram, first I have to create a data frame, then load the library ggalley, and then use the command gps. So, you can see here you get here this type of graphic, and after that if you want to get here these values for fitting the models. So, I can say here you are getting here this thing. You can see here these are the values of here alpha hat, beta 1 hat and beta 2 hat that you have obtained here, right. So, now you can see here that it is not a very difficult job to fit such models, but the main challenge in real data lies that when you have more than 2 or more than 3 variable, large number of variables affecting the process, then in that case how are you going to take the final decision that there is a linear relationship between y and all x1, x2, xp. For that, this is one way out, that I try to take the information in 2-dimensional plot, 3-dimensional plot, one variable at a time, 2 variables at a time, and finally our objective is I have to get an answer in terms of yes and no. And finally, I have to decide, yes, there is a linear relationship, then I can fit this linear regression model. Many times you will see that people simply take any data and they just try to fit the multiple linear regression model, become very happy that I have got this model, but then that model will not give you the correct answer when you want to do the forecasting and if you want to use it for some other purposes. So, my objective in this in these 2 lectures, today's lecture and in the last lecture, was just to show you that whatever the tools in EDA you have used, how they can be represented and used to find out a relationship among the variables. right? But it's a very elementary lecture, I can tell you. Please don't consider that as if I have told you all the intricacies of the statistical modeling. It requires something more. But yeah, somewhere you have to start. So at least now you have got this idea that if you are confident, you may not be knowing the algebraical part, but at least computationally you know how to get it done and how to interpret it. You can also judge whether the results are going to be correct or not. So now my request to you is that please try to take some data set and try to use this command here lm, and in that data set try to take more than 3 variables, and then try to use different types of graphics, whatever you have learned in the last so many lectures in this course, and then try to see how those graphics can be helpful in finding out the hidden information inside the data. It's not only the topics which we have covered in this lecture, but there are many more graphics which can help you in getting the correct information from the data. So my request will be that please try to practice them. The practice only will make you a good data scientist. Now you can see that in real life the complications are going to increase, but the tools are the same. And based on that you have to take the correct conclusion, and it depends only on your practice and experience that how good you are in diagnosing the problem and implementing the right solution and then getting the right conclusion. So you please try to practice, and I will see you in the last topic of this course in the next lecture. Till then, goodbye.